American vessels that crossed the sacred reef as if it did not exist and landed troops directly upon the beach without winging. The casualty statistics tell the story. Of 5,000 Marines committed to Tarawa, 109 died and 21,001 were wounded, a 60% casualty rate, the highest of the Pacific War. But analysis of casualty patterns showed men landed by Higgins boats within 50 yards of the beach had a 40% casualty rate, while men forced to wade more than 200 wide suffered 75% casualties. The difference was the boat. Later assaults, Kwajalein, Saipan, Uima, showed similar patterns. Get close to the beach fast and you lived. The Higgins boat got you close. This wasn't accidental. Andrew Higgins came from a world where boats either worked or your cargo sank, your timber rotted, or your rum got confiscated. Born in 1886 in Columbus, Nebraska, Higgins left school at 14 and drifted through lumber operations in Alabama, Mississippi, and Louisiana. By 1930, he was running a boatyard in New Orleans, building specialized craft for oil exploration, trapping, and quietly rum running. During Prohibition, the Louisiana bars taught brutal lessons. Water was shallow, muddy, and full of snags. Sandbars shifted daily. A boat that couldn't push into a mud flat, reverse itself out, and keep running wasn't worth building. Higgins developed his Eureka boat in 1926 for exactly these conditions. It featured a flat bottom for shallow draft, a protected propeller for snag resistance, and a semiplaning hull that let it back off obstacles under power. Bootleggers loved them. They could navigate waters too shallow for Coast Guard cutters. Oil drillers loved them. They could reach remote drilling sites in swamps. Trappers loved them. They could push through marsh grass that stopped conventional boats. None of those customers cared about naval architecture theory. They cared whether the boat went where they needed it to go. What made this work wasn't any single feature, but rather an integrated design philosophy. Build for the worst conditions, not the ideal ones. Naval architects designed for blue water, established harbors, and maintenance facilities. Higgins designed for mud, chaos, and zero support infrastructure. That meant simple construction, plywood and nails that any carpenter could repair. It meant redundancy. Multiple watertight compartments so one flooded section didn't sink the boat. It meant accessibility. The engine was mounted amidships under a removable hatch. A mechanic could reach every component without tools beyond a wrench and screwdriver. It meant robustness. Wooden planking could be split, splintered, and hauled, and the boat would keep running. Marine Corps Commandant General Holland Smith understood this immediately when he first saw a Higgins boat in 1940. Smith had studied amphibious warfare since 1921 and recognized that the technical problem wasn't naval. It was logistical and tactical. You needed to move large numbers of men and equipment from ship to shore quickly, repeatedly, and survivably. The Bureau of Ships approached this as a ship design problem. Higgins approached it as a materials handling problem. Ships need to be elegant, efficient, and long-lasting. Cargo handling equipment needs to be fast, simple, and robust. The Higgins boat was cargo handling equipment that happened to float. Smith forced a competitive trial in May 1941 at Norfolk, Virginia. The Bureau of Ships entered their latest design, a steel-hulled landing craft with protected propellers, a deep draft displacement hull, and a crew of 4. Higgins entered an LCVP. The test course included obstacles, shallow water, a simulated beach assault, and timed loading, unloading. The Bureau boat performed exactly as designed. It handled waves beautifully, tracked straight, and looked professional. It also grounded 50 yards offshore, required 20 minutes to load troops, and damaged its propellers on underwater obstacles. The Higgins boat looked like a lumber barge, wallowed in swells, and made alarming noises crossing the obstacle course. It also bead directly on sand, loaded 36 Marines in 90 seconds, and emerged from the obstacles with propeller intact. Smith recommended immediate procurement. The Bureau stalled for 8 more months until Pearl Harbor forced their hand. The Japanese military studied the Higgins boat carefully after capturing several intact examples in the Philippines in 1942. Their analysis recovered after the war reveals how completely it violated their expectations. Japanese naval architects had designed their own landing craft using conventional principles: keeled hulls, protected propellers, and deep draft for seaworthiness. Their Datsu-class landing craft drew 4 ft of water, required beaches with specific gradients, and cost twice as much to build as an LCVP. A Japanese intelligence report from March 1943, translated by U.S. forces after the war, noted with evident frustration: "The American landing boat is of primitive construction, apparently designed by persons unfamiliar with naval architecture. The flat bottom provides no directional stability. The exposed propeller is vulnerable to damage. The shallow draft suggests it cannot operate in ocean conditions." Yet these boats successfully landed troops at Guadalcanal through surf that should have capsized them. They crossed coral reefs that should have destroyed their propellers. They retracted from beaches under fire when our intelligence predicted they would ground helplessly. Either American sailors possess superhuman skill, or our understanding of landing craft design contains fundamental errors. The report continued with detailed technical observations that reveal how deeply the Higgins boat confused Japanese military thinking. "We destroyed one boat with 75 fire at Tagi. The shell penetrated the hull in 3 locations. We observed the boat continue operating for at least 15 minutes afterward, completing its mission before sinking. Our Datsu craft would have sunk immediately from such damage. We conclude the American boat contains some form of compartmentalization or flotation. We do not understand." They were half right. The LCVP had watertight compartments and built-in flotation, but the real answer was simpler. Plywood doesn't tear like steel. Holes are localized. You can stuff a life jacket in the gap and keep running. Japanese defenders at Saipan in June 1944 faced 700 Higgins boats, delivering 30,000 Marines across reefs and beaches they'd fortified for 2 years. Lieutenant General Yoshitsugoto, commanding the defense, had positioned his artillery to create killing zones at predicted grounding points 200 to 300 wide offshore. The Higgins boats crossed those zones in less than 2 minutes and beat in areas Seato had considered inaccessible. His after-action report captured when U.S. forces overran his command post expressed shock. "American landing vessels penetrated to positions we believed impossible for watercraft. They delivered troops and tanks to beaches we fortified only against infantry approaching on foot. The defensive plan collapsed because boats went where boats cannot go." More telling were interviews with captured Japanese soldiers. Corporal Masao Yoshida, captured at Tinian in August 1944, told interrogators, "We were trained to shoot Marines in the water as they waded from their boats. At Tinian, there were no Marines in the water. The boats came to the sand. The doors opened. Americans with flamethrowers were shooting fire before we could aim our rifles. We expected minutes to kill them. We had seconds." The Higgins boat had collapsed the killing zone from a long exposed wade to a short deadly sprint. Japanese defensive doctrine built around that wade became obsolete. The strategic impact came from production capacity. By 1943, Higgins Industries operated 7 plants employing 25,000 workers, 50% of them women with no prior shipbuilding experience. They produced LCVPs at a rate of 700 per month. 1 boat every 90 minutes, 24 hours a day. Total production from 1942 to 1945, 23,398 boats. The Navy Bureau of Ships, using steel construction and traditional shipyard methods, estimated they could build perhaps 200 boats per month in existing facilities. To match Higgins' output, they'd need to construct 35 new shipyards, train 175,000 skilled workers, and requisition steel allocated to destroyers and cruisers. The plywood construction made this possible. Each LCVP required 1,200 board feet of marine plywood, 800 lb of white oak framing, 400 lb of fasteners, and minimal steel, mostly for the engine mounts and ramp hinges. By contrast, a steel landing craft required 12 tons of plate steel, specialized welding equipment, and skilled labor that took months to train. Higgins hired carpenters, furniture makers, and house framers. He gave them 3 days of training and put them on the assembly line. Quality control came from the design. If parts didn't fit, they didn't go together. If the boat didn't float level, you'd see it immediately. Traditional shipbuilding required years of apprenticeship to read blueprints, judge tolerances, and avoid mistakes that might not show up until the ship launched. This wasn't accidental. Higgins designed for mass production from the start. The LCVP had exactly 12 major assemblies that could be built on separate jigs and brought together at final assembly. The bottom panel, the bow ramp, the engine housing, the stern assembly, and the 8 side sections were all modular. A crew could replace any damaged section in under 4 hours using hand tools. More importantly, quality didn't depend on individual craftsmanship. It depended on jigs, templates, and foolproof assembly sequences. Workers didn't need to understand naval architecture. They needed to follow instructions and check measurements. The cost differential sealed the argument. In 1943, an LCVP cost $8,500 to build, including the engine, ramp system, and armor plating. A comparable steel landing craft cost $14,200. Over the war's production run, the plywood construction saved the Navy $135 million in direct costs, enough to build 15 destroyers. The real savings came in time and flexibility, when assault planners needed more boats for Operation Overlord. Higgins increased production by 40% in 3 months by adding a night shift. Steel shipyards needed years to expand capacity. Combat damage reports validated the construction choice in brutal detail. From July 1943 to August 1945, the Navy recorded 2,847 LCVPs damaged in combat.